Well, the shaper is in pieces over there because I had a couple of small improvements. Improvements. Hello, Internet. My name is Quinn, and this is Blondihacks. Well, the shaper is in pieces over there because I had a couple of small improvements that I wanted to make. And here's the thing. Once you start looking for problems, you're going to find them. And let me just say, this escalated quickly. So let's go. Regular viewers will recognize my Atlas 7B shaper, which I believe from the serial number is roughly 1961, which makes it about 65 years old. And it's had who knows how many owners, but I'm the current owner of it, and it was donated to me by the wonderful folks over at the Hamilton, Ontario Model Engineering Club. Thanks again, gents. And it's been a trooper for me. I've had lots of fun with it, but going on about a year now of making chips with this thing, and I've got a few little improvements that I want to make. The first is an easy one. When I first got this thing, it had the old brick-on-a-leash light switch for power, which was a common thing that folks did, especially like in the 70s when these machines were often remotored when the first motors in them went out, and the wiring maybe was fabric wiring, not very good, and so it was easier to just throw a light switch in a utility box on the outside of the machine. But I replaced that and redid the original internal wiring that the machine had. However, I couldn't get the kind of super low profile switch that the original would have had, because there's only about a 1/4 inch of depth behind this casting before the back of the light switch would hit the bowl gear inside. So I 3D printed this boss to allow me to put a switch that was further out and maintain the original look and feel of the machine. It's also just super handy having the power switch right here next to the clutch handle, which of course was Atlas's intent. This 3D print has served me very well and it's worked fine. However, a viewer was doing some foundry work and he was like, hey, if you send me the STL file for that 3D print, I can make a pattern and cast it in iron. And he did, and look at that. He even machined it for me. This is actually a really cool example of the differences in manufacturing techniques. So on the 3D print, I was able to simply print that inside square pocket for the body of the switch. However, in machining, that's what we call an unmachinable feature. You cannot machine a perfectly square inside corner like that. So what he has done is what's often called mouse ears or dog ears, which is a plunge cut in the corners, which eliminates the fillet that would be there from the end mill and allows you to seat a rectangular object perfectly in a machined pocket. It's not something you see a lot these days because we have other manufacturing techniques. You might see that done with EDM today, but well, back in the day, you see mouse ears everywhere for situations like this. But this is an easy upgrade, and amazingly, he did an incredible work on the foundry pattern for this. It fits absolutely perfectly, like it's to the 1000th identical to the STL file that I sent him. And how class is that? That is just fantastic. I'll find the right paint color for it to try and match the rest of it, but for now, look at that solid cast iron switch boss. Just beautiful. The machine deserved that, it really did. Moving on, I'd like to have a look at the handwheel marking collars. The way that these handwheels work on a machine without a DRO is that you feed over until you have a touch off with your cutter or an indicator or some other form of edge finding, and then you want to zero the hand wheel in that position. So you rotate the collar till the 0 lines up, and then you can lock it down, and then now from here you can start measuring your cut. If you don't have the ability to spin and lock the collar like that, then you have to do a bunch of math from wherever the touch off happens to land. The problem is, because it's a set screw on this machine, it's not a friction fit or a thumb wheel, then if the set screw happens to land on the underside of the dial after you do your touch off, well, you have to do a maneuver like this to find the set screw so that you can lock or unlock that hand wheel without moving it. And no, I know you're thinking of other ways that a person could do this, but trust me, there is no possible other simpler way to do this besides this comically ridiculous thing that I'm definitely not hamming up for the video. There's no possible way to do it any other way, including dropping the screwdriver on the floor. That part was key. When I look at pictures of other Atlas 7Bs online, if you look really closely at a lot of them, they actually show a thumb wheel there instead of the set screw. So this may have been a thing on some of these machines. It would certainly be a lot more convenient. So I did a little more digging. When you look at the parts diagram, however, it does show something that they call a collar screw. It's not obviously a thumb screw in the drawing. It's hard to tell, but it is definitely a screw with a head on it at least. It's not a set screw. And we know it isn't because elsewhere on the parts diagram, they use the term set screw. So if it was supposed to be a set screw, it would say set screw. However, counterpoint, if we go and look at the tool head does have a set screw there. So maybe one of them was supposed to be a set screw and one is a thumb screw, or who knows? It's really hard to say on these things. And these parts diagrams are not infallible. Like, they change the design of these machines during manufacture all the time, and they didn't always go back and update the parts diagrams. So who knows? These machines varied a lot. They were all handmade at the end of the day. But I'm going to replace them with a thumb wheel, so I need to check how much room I've got, and I checked the thread that I've got in there. This is not quite a complicated enough part to be worthy of getting out CAD, but I do like to do a little sketch so that I don't lose track of what I'm doing over on the lathe. And let's turn a little thumb wheel out of brass. I think I can turn something just large enough in diameter to give me enough torque to lock that by hand and not need a tool. You don't really need very much clamping force on those little collars. There's very little torque required, so a small diameter knurled thumb wheel should be okay. I also chose brass because then it can clamp down on whatever's behind that graduated collar without marring anything up. I'm leaving a plain shoulder above the threads a little bit, and that's to have the knob stick out past the surface of the collar a bit, so you have some kind of clearance to kind of get the sides of your fingers around the back of the knob, if that makes sense. You can't have a knob that's flush to a surface. That's too awkward. Put a nice chamfer on that because chamfers are what separate us from the animals. And then I'll bring in my knurling tool and we'll put a nice heavy knurl on this. I'm actually not a huge fan of knurling in general. I know most people love it because it is pretty, but it is also quite hard on your fingers if you have to use it a lot or if it's in a situation where you have to apply a lot of torque. However, in this case, I think it's the perfect application for knurling, and in fact I want quite a heavy knurl on this because this small diameter means it's going to be more difficult to get a grip. This knurling tool, if you're interested, was built from a kit. I have a video series on building this. It's from D. Gray, Drafting and Design. It's definitely the best knurling tool that I've ever used. None of them are frankly great knurling tools, but this is the best one I've used. It was a really fun project to build it, I will say, and the versatility of this is really nice. It works on a very large range of diameters, and it gives very consistent results because you can put a specific angle of turn on that nut with a wrench and it'll produce the same knurl every time. And of course you always chamfer the sides of a knurl, both because chamfers are what separate us from the animals, and also it makes the knurl a lot more comfortable and better looking. And Gatsy. And it turned out quite nice, that little guy, so let's thread that in there and see if it functions. This is an open question whether the diameter is large enough and whether it's going to clamp sufficiently well to be reliable. So there it is loose, and then if I put a little angle on that, yeah, look at that. Clamps down, and then once it's clamped, it spins nicely with the crank. So that seems to be working very well. It is a tiny bit fiddly because it's not sticking out very far. If it was sticking out further, you could get a better grip on it. However, if it stuck out further, it would really be swinging around a lot and it would tend to catch on things and be in the way. Plus, you'd have to be careful to make something that clears these bolt heads, so it would have to be quite thin in the shank area, and I don't know, I think short is probably the way to go. However, there is one side effect I did not anticipate, which is that the head of the knob blocks some of the markings on the hand wheel. Now, fortunately, I got lucky here. You can actually see the 0 and the 90 on either side of it, and really the 0 is the only one you generally need to see because you want to be able to zero that, and then you're going to be moving clockwise from there. And luckily, as I said, the diameter came out just right that it missed both of those two markings. So dodged a bullet there, but that's why tool design is hard, because there's always little side effects of things like that you didn't anticipate. That seems to be okay though. So I made a second one for the other hand wheel, and the other hand wheel worked even better because there's plenty of clearance around this one, so it's not difficult to get a good grip on it. The next change is going to be to do with the gib. If you watched my unboxing video on this machine, you know that when I got it, the gib on the tool head was extremely tight, like way too tight. So I loosened it up to normal tightness, and I used it for a while that way, and then found that the problem is that the cutting forces would tend to push the tool head up. So then I was like, oh, that's why the previous owner had that gib really, really tight, is to keep the cutter from pushing it up while it's cutting. However, that's not really a very good solution because a really tight gib is going to wear out the dovetails and the lead screw nut over time because you're putting a lot more force on them. The ideal solution is to have the gib looser, just tight enough to where things slide without having any play in them, and then you have a slide lock on that gib that allows you to lock it up when you're cutting, especially when you're doing an important cut. And weirdly, the tool head on this machine does not have a lock on it. That honestly seems like a design oversight from Atlas. In my humble opinion, it's never a good idea to have a slide that's going to be subject to cutting force pressures that does not have a lock on it, because obviously that slide is going to move under heavy cutting. It's unavoidable. So what I want to do is add a slide lock to this machine. It's a pretty simple modification that you can make. It's quite an easy job, really. I'll just get this tool head off here. And, you know, as I was getting ready to crank the tool head off, this tool head has a lot of backlash in the lead screw, and it always has since I've had it. And I never really thought too much about it, but you know, let's just take a quick look at that, because that's like 30 thou of backlash, which is a lot even for an old machine. So since I got to take the thing off anyway, let's take a look at that and see if it's something that we can address. So loosen off all the gib adjusters and crank the thing off of here and take it over to the bench and have a closer look-see. While I'm here, I should fish the lead screw nut out of there, because if there is a backlash issue, it's usually caused by a worn lead screw nut. However, it won't come out due to some burrs on the end of the thread, so I gotta unbolt the tilt mechanism, and oh my goodness, that one bolt was completely loose. So guess we better have a look at that while we're in here too. Add that to the side quest list. But if I pull this tilt mechanism out, then I should be able to tap the lead screw nut all the way through. I can't really get the burrs off of it any other way, so as I tap it through the cast iron, the bronze burrs will fold over. It won't hurt anything. I don't like hammering things apart, but yeah, sometimes it's necessary. I will also mark the orientation that it came out of, both vertically and end-to-end, so it can go back in the same way just in case, make sure the wear stays consistent. Then I'll thread it onto the lead screw, and let's just see if I can feel where the wear is in it, or if there is wear in it. If it's really bad, you can feel it in the nut, but honestly, like, that feels okay. I mean, there's a little bit of movement in it, as there always is in a lead screw nut. There has to be. And there's a little bit of tilt in it as well, which is indicative of possibly the hole being ovaled out a bit. But honestly, like, it's not that bad. It's not brand new, but I've certainly seen worse. Out of curiosity, I have an Acme thread pitch gauge, so let's just see what this lead screw is. And yeah, it's 10 threads per inch and 1/2 inch diameter, so it's a 1/2 10. Interesting. That information is not useful. I was just curious. Now, I'm not going to make a new lead screw nut for it. I'd have to order this special tap, and oh, wait a minute. I own exactly one Acme thread tap, and wouldn't you know, it's 1/2 inch 10. Wow, what are the odds of that? Huh. Crazy. This is literally the only Acme tap I own, and it's the exact one that I would need for this job. But I'm not going to do it because I don't have the material. Oh, wait, I found this perfect piece of phosphor bronze in the bin. All right, the universe is telling me to make it a new lead screw nut. So here we go. Over to the lathe. It's a very simple part, at least. Should only take about 10 minutes to make it. So I'll start by facing off the end, as is tradition. This is phosphor bronze, which is a very good choice for a lead screw nut because it's very, very tough. Phosphor bronze is like the forbidden love child of bearing bronze and tool steel. It's slippery like bearing bronze, but it's really tough. It cuts like tool steel. So I use the tool geometry of bronze, but the feeds and speeds of tool steel. You can see me taking light cuts, and you can see the cutting smoke pouring off of this thing. That tells you how tough cutting this stuff really is. You got to take your time and take light cuts. It's surprising that bronze can be this tough. A good old PB1, it is tough stuff. I don't like machining it, frankly, but luckily this is a very simple part. We don't have to do much to it, and it really is an excellent choice for this material. I made it a couple of tenths larger than the factory one just to make it a little closer fit in there, because if there's any slop in that fit, then that will also introduce backlash into the system. So the hole in the cast iron part could be a little worn out, so a little snugger fit's not a bad thing. Then while it's still attached to the stock, I'll use that to fixture it in the mill so I can do the drilling and tapping. To position the hole, I need to know how big the part is, and this is actually pretty interesting. So the length of the part is 755.5, but the diameter of this thing was dead nuts 750. So that tells you kind of an interesting story about the manufacturing tolerances that they probably had at the factory. The diameter of this would be critical, as I said, so it doesn't have backlash inside the housing, but the length of it is actually quite a bit more flexible because the nut can slide back and forth inside that cast iron housing. Precision costs money, and larger tolerances make for cheaper manufacturing of a part. So a manufacturer is going to want to have the loosest tolerances they can on a given part. So if a tolerance can be 5 thou on a part, they're going to make it 5 thou on a part because they can cut them faster, make them quicker, and make them cheaper. It's also entirely possible that this is off dimension simply because it's a shop-made part that someone before me made. I mean, this machine is 65 years old. This may well not be its first lead screw nut. This might be its 10th one. We don't really know. But anyway, with the drilling out of the way, now comes the fun part, the Acme tap. Now I have a giant tap wrench, but it's too big for this tap. So believe it or not, this small one is the correct size for the boss on this tap. The drive tang on it is not very big. And it probably should be bigger because if you've never used an Acme tap, let me tell you, they are no picnic. There is a lot of tool pressure. They make them really, really long to try and make the cut as progressive as possible, but even with that, it's still, these things are a lot of work. Lots and lots of cutting oil helps, and it's pretty easy at the start, and like most taps, it's easy at the end again, but in the middle, there's a section where it's really getting difficult, and I gotta put some gloves on. This is not too bad because it's bronze. The reason I own this tap is because I used it to make my float lock vise, and the jaw on that was steel, so I had to run this tap through steel, and that was way harder than this, actually. I had to put little cheater pipes on the tap wrench because I couldn't move the tap. It was such high tool pressure. This is not too bad. I mean, you can see me making exertion faces there, but it's not as bad as the steel was anyway. Fortunately, I had just about enough room in this vise setup to get that long tap all the way through. The way these taps are intended to be used is you're supposed to feed them all the way through the part to guarantee that you get the right thread geometry all the way down, no matter how tall the thread on the part is. I didn't quite have enough room, but I got far enough that I don't have to worry about taking it out of the vise. I can just take it over to the bench vise and finish running that through. And right at the end here, of course, it gets easy again as we're into the straight part of the tap. All the taper sections have done their work, and we can thread that all the way through. So that actually wasn't too bad, much easier than steel for sure, and look how nicely that came out. That is quite a beautiful looking Acme thread. Acme threads are wonderful things. A lot of work to create and a lot of work to deburr because the geometry that's created when you intersect an Acme thread with a cylinder is cray-cray. Do it in CAD sometime if you want to see what this looks like. You get all manner of crazy little cliffs and overhangs and like holes in the side like you can see on the factory one. They didn't make much of an effort to deburr this in the factory one or whoever made this nut. You can see there's fragments hanging out everywhere. But I did a little better job of deburring mine at least. I took off all the sharp edges and the thin areas and the loose bits. But you still end up with a crazy shape. Now I can part this off. The factory one had generous chamfers on both ends, so I'm going to replicate that detail. It will make it easier to slide the thing in and out. And the nut actually may want to slide in and out in that casting as it moves up and down. Like if there's any slight bend or anything in the lead screw, having the nut be able to slide fore and aft a little bit is probably a good thing. So a chamfer will help with that too. There we go. It's shinier than the old one, but is it better? Well, let's find out. I'll snug that into place and I'll thread the lead screw back in there. I'm oiling everything up, of course, as I reassemble. I don't always show this, but I always oil everything before I reassemble it. People sometimes get mad if they don't see it happen, but it happens. So slide that down there and thread that in. And I did a kind of a preliminary snugging of the gib. It's not perfectly adjusted, but already that is night and day better. Honestly, the old one didn't seem that bad on the bench, but I'm actually having trouble detecting any backlash in that now. It's responding beautifully. You can see the smile on my face at how nicely that's moving. You saw it wobbling there because the gib isn't tight, but don't worry about that for now. Let's move on and do that slide lock because I do still want to do that. So someone's been in here before, interestingly. There's a Sharpie mark on one of the gib ends, which is good. That tells me which way that goes back in. I decided I could clamp it up in the mill vise like this. The lead screw is not being bent or anything. It's not touching anything. And by taking the tool holder off, I've got two parallel surfaces opposite between the bottom of the dovetail and the top of the clapper box. So this made for an easy clamping setup. Then I used a gauge pin to locate two of the gib clamping threaded holes. That gave me the Y position of where these are, which is going to be a good spot on the gib. I know that because these screws are already clamping on it. Then I used the half function on X to get halfway between them. I actually did a test on the machine, and I found that if I put this lock right in the middle, it will stay aligned with the dovetail on the ram throughout the entire travel of the lead screw. If I put it anywhere other than right in the middle, then there will be a portion of the travel where this screw is above or below the matching dovetail, if that makes sense. So it wouldn't have locking functionality in all positions of the tool head. It's really all there is to it. Drill and tap a hole somewhere on the slide and put a bolt in it and you've got a lock. However, I'm going to go a little further. I'm going to transfer punch that position on the gib because I want to mill a flat spot on the gib for the screw to push on. It's best practice to do this if you can. You'll notice that the factory gib adjusters all have that flat spot. Now that flat spot's at a 30-degree angle because of course the gib sits at an angle. So I'm using my angle table for this, and then I go down in there with a end mill and I plunge a little flat spot about half round, which is the same depth as the factory ones. If you go too deep, of course, you risk breaking through the upper end of the angle. And I figured the factory ones are a good guide for how deep to go, so that's what I did. And I made it the same diameter and same thread as the gib adjusters as well, just so I could copy what the factory had done there. And that is a nice little flat spot for the bolt to push on. It will lock much more effectively and much more consistently and repeatably with that flat spot. Now, I'll skip through making this big knob because I thought, oh, I'm going to make a brass knob just like the little thumb screws because a brass knob will look nice and I can use that to lock it down. But I didn't want to knurl it because you can't really get enough torque on a knurl without hurting your fingers. So I thought I'm going to make a scalloped knob instead because that'll give me much more force without hurting my hands. My thought was I'll cut those scallops by plunging with an end mill, and I'll use the bolt circle function on the DRO to space them around the outside. This is a common way people make scalloped knobs. However, I knew this setup was going to be a little sketchy because the cutter turns clockwise, so it's going to be putting counterclockwise force on the part, which is going to want to unthread it. It's going to be trying to loosen that. And I thought, well, I'm going to be taking pretty light cuts, and if I gronk down on this thing real good, then I think it'll probably be okay, right? Should be fine. It was not fine. Okay, that was admittedly a very stupid thing to try. Of course, that's what's going to happen, but no real harm done. I'm going to cut away all of that damage anyway, so I'll just add a clamp. And that should be enough, right? That should be fine. Yeah, that was even less fine. Now I've really messed it up. Sometimes I shouldn't be allowed to get out of bed. I don't know why I thought that was going to work. Again, of course that's not going to work. That's a stupid setup. Don't ever try that. Well, it's knurled now, not the way one would want, but yeah, no, that cut sent it from mostly scrap to definitely scrap, because now it's even bent and the outside of it's all mangled. Yeah, I deserved that for trying that setup. However, it's kind of a good thing because I did a test fit with the mangled remains of the part, and this wasn't going to work anyway. First of all, that 1-inch knob is just really not enough to get enough torque on that gib to lock it up. It's a pretty short and thick gib, so it takes a fair amount of force, and I wasn't going to be able to do it with that little knob, and the knob is going to interfere with the clamping bolts on the tilt mechanism, and you can't really get your hands around it. So to fix all of those issues, I was going to have to make it stick out further from the casting, but it would have to stick out so far that it wouldn't be very strong, and it would be catching on things and kind of be in the way. So I decided, you know what, I'm overthinking this, over-engineering it and under-executing it. I just went ahead and put a bolt in that hole, and I will use an Allen key for tightening it. This is how the cross slide works on my lathe. I've had it for 10 years that way, and it works just fine, honestly. So you can lock it up easily, you get all the torque you need, and I have zillions of spare Allen wrenches, so I just put one of those next to the machine, and that's how I lock it up when needed. So I took that screw out, and I put a little dog point on it. A dog point's always a good idea on a screw like this because it gives you more clamping force for less effort because it concentrates the force on a smaller area, and it guarantees that the end of the bolt isn't going to mushroom out and get stuck in the thread. The end of that dog point can mushroom, and it's never going to get larger than the thread. Well, there you go. Ill-conceived and poorly executed. So long, brass knob, you were a beautiful dream. Incidentally, Ill-conceived and poorly executed is the name of my autobiography. That job done, I was getting the gib all adjusted and pretty pleased with myself. Good day's work. Everything's fixed now that I wanted to fix. And then I noticed, you know what? Look at that. I never noticed that play before. This actually explains something I've been noticing in my cuts, however. I would often dial in a 10 thou depth of cut, and I would end up getting 7 or 8. It was cutting under size. And I'm sure this is why, because the dial wouldn't be registering this upward play in the tool head. So it looks like those jam nuts need adjusting. However, here's the thing about jam nuts. They are thin. In the days before Nylock and Loctite and lock washers and all the stuff we have nowadays, these thin jam nuts were used. The idea was that you could jam them together and they take up the same space as one regular nut. However, that means you need thin jam nut wrenches to work with them. And I don't have jam nut wrenches because it's just not something you see very often these days. However, I did find some scraps of flat bar in the bin, and I can make some field expedient jam nut wrenches. So some quick work on the bandsaw and a little bit of die filer work to clean up the cuts. And these are not very pretty, but perfectly serviceable jam nut wrenches. And these will go in the bin with my shaper parts when I'm done, in case I ever have to do this again. Those two little guys should do the trick and allow me to get this apart. I'm not just going to adjust them, I'm actually going to take this whole mechanism apart for reasons that you will see shortly. Also, I just kind of want to see how it goes together. So there's a woodruff key that connects the crank to the shaft, and then the lower jam nut is setting the end float on the lead screw. So that's really the issue, is this lower jam nut. And then the upper jam nut is just clamping the crank into position. But I want to get this graduated collar off of there. Why do I want to do that? Well, you may have noticed in a lot of the previous footage that those graduated collars are very difficult to read. Now, a person could improve that by, rubbing some paint in them in the numbers, for example. However, I've got a better way. A while back, a viewer wrote to me and said that he's got an Atlas 7B, and at his work, he has access to a rotary engraver. And he didn't like these numbers either, and he wanted to make his own collars for this. And he said, do you want me to make you a set as well, since I'm doing it anyway? And I was like, heck yeah. And this is what he made. Look at how beautiful that is. These are perfectly engraved hand wheel collars. These are just beautiful, and they are so much easier to read. Very, very pleased with that. He sent me one for the tool head and one for the cross slide, which are the only two this machine needs. So taking this all apart was an excuse to install those, and now I'm going to get those jam nuts readjusted for proper end float on that lead screw. The goal is to get the lead screw to have essentially zero end float. It can't be grunked down tight, of course, because then you can't spin the collar and the lead screw won't spin properly, but you want it to be as close to tight as you can get it while things still move freely. And let me tell you, that's not easy. I'll save you the 45 minutes or an hour that I spent trying to do this. I ended up having to take it apart and take it back to the bench, and the secret was to tighten the lower jam nut to where the end float is perfect, and then put thread locker on it and hold it in place, then let the thread locker set, then put the crank on and tighten the outer nut to snug down the crank. Trying to do it the old school way of just tightening the nuts against each other without either of them moving was really just impossible. I couldn't get it to work, but now that is fantastic. Honestly, I can't even feel any backlash in that anymore. I'm sure there is some. In fact, let's put a dial indicator on here and find out, because there always is some, but I couldn't feel it. So I'll zero that with some preload in one direction, and then let's see how far I can move it before the needle moves. Survey says right, a little more right there. So we'll call that 8.5 thousandths. So call it 9 thou of backlash, which is honestly very good for a 65-year-old lead screw. For comparison, here's the y-axis on my milling machine, and that's got about 18 thou of backlash in it. It's a bit of an unfair comparison because this is a much coarser and larger lead screw, so it will have more backlash in it. Let's go over to my lathe and look at that. The carriage actually has quite a lot. That's about 25 thou, but this is an apples and oranges comparison because this isn't a lead screw. This is a rack and pinion drive on this hand wheel. Now, a more fair comparison would be the cross slide on my lathe because it's a similar size and diameter of lead screw. So again, I'll load this up in one direction, and then I can just feel the backlash in this. I don't have to use a dial indicator to know what it is. And right there. So that's 6 thou of backlash in that. Now, I know the hand wheel marking says 2 thou per tick, but that's because it's a diameter reading. The radius is what we care about, though, for backlash, and that's 6 thou. Now, interestingly, though, this cross-slide hand wheel has a backlash adjuster on the nut. I found that out the hard way when I broke it. I've crashed this lathe once and only once, I guess, proud to say. I've crashed the cross slide into the end of its travel under power feed once, and it broke the backlash adjuster. So while I was waiting for parts to fix it, I used the lathe without that for a while, and it had about 20 thousandths of backlash in it, so quite a lot. That backlash compensator is doing a lot on that cross slide feed, and so for nothing fancy like that on this tool head, 9 thousandths of backlash is pretty darn good, if I do say so myself. For a 65-year-old machine, I think it's really fighting fit now. I'm very pleased with all these changes. Wow, I'm going to enjoy this machine even more now. It really didn't need any of this, but it definitely deserved it. So thank you so much for watching. Thanks to my patrons for making all of this happen, and I will see you next time.